It's interoperable and high performance. So and also because of type inference. We'll talk a little bit more about the languages and why they're. Anybody a big Scala guy here? Scala person? Few people. Oh yeah, he loves Scala. Right. The guy that hates Hadoop loves Scala. Right. That's good. We'll get along. Question. Go ahead.
When we were talking about I/O bound processing, MapReduce in particular, there have been sort of advances in the HDFS caching where at the block level, it can be keeping data sets in memory longer. Do you consider that to be a possible solution?
Yeah. Sure. Caching always helps. You know, of course, Linux does caching. There's a lot of caching that goes on in a lot of places. Yeah, that can help. But unfortunately, caches they really don't know anything about your data. They really don't know anything about how you're running your process. So yeah, they help. They're better. But still, the more you know about your algorithm, the more you manage that memory yourself, the better off you're going to be. So yeah, it helps. This product that I was showing you about earlier, it would help even more because it was largely to solve that I/O bound problem. We had very, very high data I/O rates. You know, MapR, they're working on the lower levels to improve that I/O bound. Those are all good things, but still, the abstraction is read it, process it, write it back. Read it, process it, write it back, right?
Yeah, adding cache helps a little bit, but you're just throwing hardware.
Yeah, exactly.
I mean, the main problem with MapReduce is it's the anti-schedule. The bottleneck is I/O.
Yeah.
They're saying let's do all our I/O
Yep.
at the same time, and so that's why your performance is 100th of what you're doing.
That's right.
What about Tachyon?
You mean other implementations of HDFS and all that?
No, Tachyon, right? Spark use Tachyon caching.
Right, but the thing is, it's a little bit different because not only, I mean, it'll still read and write, but it can use memory. And in fact, you could use all the memory you've got. How much memory does MapReduce use? Absolutely none. By default, it uses none of it, pretty much. If you use distributed cache, yeah, you can start using it. If you start sort of caching it yourself, you can use more memory. But then you're the one that has to do that. But at the end of the day, nothing stays in the mapper. Right? None of the intermediate results stay in the mapper. They've got to go out. None of the intermediate results stay in the reducer. They've got to go out. Right? It's not done that way. It's not a fault of the. I mean, it's a great idea. It works, but it's not. It's got its limitations. Right? That makes sense. Okay. And I've run those numbers. I in fact, whenever I run any of our jobs, I measure it and I look at it and I see if it squares with the hardware, what the hardware capability is. And for the most part, that it comes out to that. I was often surprised how accurately it pretty much comes out to those numbers that I tell you about. It's a good way to estimate also. So if you're going to build a cluster, you're going to ramp up something in Amazon, something like that, you can have a pretty good idea of how much I/O you're going to need to process a certain amount of data in a certain amount of time. Okay? A little bit of arithmetic goes a long way. Okay, so yeah, question? No. All right, so a little bit, here's a picture of what really happens, and this might explain a little bit of why it comes out better in Spark. Okay, so let's say in HDFS I've got a bunch of blocks, right? A typical HDFS file, each one, let's say 64 megabytes, 128 megabytes, whatever you like, however you configure it, right? So in Spark, I have that this SC, which is Spark context, and I can call this text file method and tell it to read in this in.txt Hadoop file. It could be terabyte, could be huge. All right, that returns an RDD, right, which is like an array list or an iterator or something like that. So really, under the hood, what it'll return is an instance of that, which is Hadoop RDD. That Hadoop RDD has a bunch of partitions in it. All right, you see those green blocks are these partitions. All right, so what that does is it take the data and split it up. All right, the simple way by default, if you just read a Hadoop file, it'll break it up by the number of blocks. All right, yeah, let's say that for now. There's other ways to break it up, but by default it'll do it by blocks. So let's say there's 64 megabyte blocks. All right, and inside of each of those blocks are going to be individual objects. Right, by default the text file is going to just break it out by new line, just like you would see in like a text input format in Hadoop. Okay, so that's simple. So given that RDD, I can apply one of the transformations like filter, and I could pass in a function. I want to filter by lines that contain Spark, right? That'll return another RDD called filtered RDD, all right? And from that one, I can apply a map function, I apply a union, a group by, whatever. Where did it write to disk in that process? Do you see any disk writes in that process? Right? You don't see any. Now, presumably there might be. It all depends on how much memory you've got and how big your data is. If your data fits in memory, it'll never go to disk. It'll just sit in memory. And you could just keep performing operation after operation after operation. So you're getting pure memory performance. So yeah, cache could help, but this is better, right? Because you're not dealing with the cache. You're dealing with straight memory. Right? Of course, it does degrade over time. You eat up all memory, then yeah, it's going to go back to disk. But the nice thing is it gracefully degrades. And I got into a lot of how that's done, of how the memory management's done, and it's not trivial. It uses these memory fractions. It tries to keep certain amount of memory free and available. And when it gets to a certain point, it starts spilling data to disk. Okay? So, yeah.
So what are these things called one-to-one? These are blocks in...
Those are partitions. So what the blocks were, you see there are n blocks on the left? They effectively turn into n partitions in the RDD. Effectively, they're one-to-one, yeah.
They are on the same computer?
Spread over the cluster, okay? So let's say I have 100 blocks and I have 10 nodes. Each node's going to have 10 blocks or 10 partitions, uniformly distributed.
Yeah, my question was, if the block 1 is on computer 1, then this partition 1 would be on the same computer, or it can go to other computers?
Just think of it that way. Without, like, where a specific block is doesn't really matter, right? It just matters that it's uniformly distributed. That's the critical part, right? Because you want all computers to be, you don't want all the blocks on one computer, right? Because it's, right? So as long as it's uniformly distributed, like let's say that I do that map function, right? Or the filter function. So internally, what is it going to do? It's going to tell all the nodes, go and filter your data. Go and filter your partition, right? So they each perform that filter operation on the partitions they know about, okay? And they keep it in their memory, right? They may spill it to disk if they have to, but for the most part, they'll try and keep it in memory.
And they continue to be independent on different...
They're independent, right? They're independent. Now, the place where it is not independent is when you get to something like a group by, or you get into some of these other things where you have to do a shuffle, where there has to be network exchange, okay? So there are certain operations that cause that. Map, filter, union, so on, do not require that. Those are simple one-to-one, right? Oh, no.
Oh, if people have questions, do you mind speaking in the mic?
Yeah.
Because we're videoing, and so we can pick you up if you don't mind.
Yeah.
So I'm going to pass it on.
Okay. All right, any other questions, comments? No? Okay.
There's a question. I think there was a question.
Yeah, go ahead.
I've been told that spillover to disk in Spark actually can cause Spark to grind to a total dead halt. Is that true?
I haven't seen it. I'm sure if you want to kill it, I'm sure you can. If you try hard enough, you can. But you can do that with MapReduce just as easily, right? You know, one of the simple ways like whenever we saw our jobs running really, really slow, it's because we had something wrong with the data and all the data piled up on one node, right? And you'll kill it, right? And so that same thing can happen with Spark. So one thing to keep in mind, you know, you can overstate it, and you could say, oh yeah, it'll solve everybody's problems, you know, cure world hunger, you know, there'll be no wars and all this stuff, and it'll be Star Trek utopia. No, it's not, right? But it's better, is what it is. So so have some idea of what's going on inside. So and hopefully some of this will help to get a picture in your mind of what's really going on, right? And once you have that picture, you have a better idea of how to keep it from falling apart. Go ahead.
So HDFS versus RDD, do we need like higher memory for?
More is better.
Okay.
In big data, we say size matters.
No, that's true, but do we need, because we are using Spark, or can we use the same?
More is
computers?
better.
Okay, that's
Right.
fine.
Right? So it's all money trade-off, right? Time is money, right? If you want it faster, it's going to cost you more. Buy more nodes, buy more memory. There are Amazon nodes that have massive amounts of memory. What's that? Some of those big instances that they have in Amazon that? Yeah, you can get some nodes in Amazon, 196 gigabytes of RAM, right? So if you want it really fast, and Hadoop it won't use that memory, so there's really not much use in it. But if you do that with Spark, a terabyte, you get about 10 of those nodes, you pull all that in memory, right? And it'll work well, right? Yeah. Okay, so you see each of these operations, and at the end, you can do a save, or let's say I end up with another RDD after doing this group by all these multiple operations. And here I just did them sequentially, but you can see I could do this in a loop, right? Very important for machine learning, where you want to iterate and do all this stuff. And at the end, then I want to save that. I could save that data, okay? Put that back into HDFS. And okay, so let me show you exactly what's going on inside. Here's a trivial example, not getting into too much detail, but give you an idea of how it works. Okay, this code runs. You could copy and paste this and build it and run it. So that Spark context, I'm just going to use a trivial list of data that's made up. It's not reading from HDFS. It's just taking a list of numbers 1 through 8, all right, and it's using this parallelize. And all it does is take that data and split it up into multiple partitions. And then I specified number of partitions as 4. And I chose 4 because let's presume that even my lowly laptop has 4 cores on it, so that I could effectively distribute that data over those 4 cores just on my single computer with multiple in one processor, right? So each one will have 2 numbers in it effectively. Not a whole lot, but simple enough. All right, so that returns an RDD, right? That input is an RDD, okay? And then I'll print out the number of partitions, and it says, okay, there's 4 partitions. And then I'll call this input.map, and all it does is says take every value and multiply it by 2, all right? Trivial, absolutely trivial, nothing complicated. That's done in parallel. So what happens? Every partition will multiply its data by 2, okay? And at the end, I'm going to collect that data, meaning take that data that's spread out over these multiple cores or multiple nodes, bring it back, and print it out, because it has to be collected at some point and print it out. In this case, I'm going to collect it and print it out in the console. Yeah, correct. Okay, simple enough. That's Scala. All right. So let me tell you what's into the Spark code itself. So if you go into download the code, git clone Apache Spark, you'll go into the Spark core source main Scala org part rd.scala. Not a big file. It has nice documentation at the very top, and if you scroll down, you'll see a function called map. All right? Scala people will recognize all the U class tag, all this business. It's like generics if you're a Java guy, okay? Because Scala is strongly typed, but it does sort of type inferencing, and it uses, and particularly Spark, they heavily use this whole idea of, I guess, generics for a better word. There's probably a better word they use in Scala, but to genericize the types. So there's no specification of what type comes in. So what the map is working on is an arbitrary function. You give it an arbitrary function, that's that function f, that transforms some variable of some type t and transform it to another of some type u.